Welcome to the quantum theory evidence video. In this video, we're going to give you a couple experiments that were done to verify Einstein's theory that light has a particle-like nature in addition to being wave-like in nature. The first experiment we're going to take a look at here is called the Compton Scattering Experiment. Really was the first to prove that light also has a particle-like nature in addition to a wave-like nature. Einstein developed his theory, but to that point there really had been no experimentation or proof other than the photoelectric effect to say that this was true. Just to give you the big picture here, in order to say that light acts like a particle, that means it should do things that particles do, like conserve momentum and conserve energy. Compton was the one that was able to prove that, and we're going to show you how he did that. Before we proceed, if you haven't done so already, you should have this diagram pictured, copied into your notes, and as soon as that's ready, we can begin the discussion on this and show you how he did this and proved it. So at this time, pause the video, draw the diagram, and we'll continue when you're done. Alrighty, as you can tell here, what we have was incident X-ray photons, or in other words, an X-ray, which is theorized to be made out of photons, that is going to strike an electron at rest. This, of course, is the information for before collision. Okay, this is what's taking place before the collision. After collision, we have the photons, the scattered X-ray photons, move down and to the right in this diagram, and the electron moves off above the x-axis there, above right. Now we're going to take ourselves through the same questions as if this was a collision in our momentum unit. What objects, if any, have momentum before they meet? Well, the only objects that are moving in this diagram are the X-ray photons. And what Compton figured out was an expression for the momentum is P, and we're going to call it P1 because it's the initial. We're going to let the initial momentum be the 1 equals H over lambda. So the momentum of the X-ray photon is given by Planck's constant divided by the wavelength of the photon. Of course, our electron is not moving, so it has no momentum. And the next question we're going to ask, what objects, if any, have energy before the collision? Well, the answer, of course, once again, is the only object that's moving are the photons. And how would we express their energy? Well, we learned in the photoelectric effect that the energy of photons is expressed by HF. And we'll give that a E1 and an F1 for our initial amounts here. Also remember that another way to express that energy is HC over lambda, so that would be lambda 1 as well. So E equals HF1 equals HC over lambda 1 is our expression for the energy before collision, and P1 equals H over lambda 1 is our expression for the momentum before collision. Our electron is at rest, so it has no energy either before the collision. All right, after the collision, our electron gets shot off in one direction. And how do we express their momenta? Well, the recoiled electron would have a momentum. Of course, it has mass. So it would be P equals its mass times its speed, and it moves off with speed v. How do we express the energy? Well, it's moving, so it has kinetic energy, which would be expressed by Ke equals 1/2 mv squared. Okay? All right, next we have our photons also being scattered after collision. How do we express their momentum? Well, we would say P2, because it's not the same momentum as before, equals h over lambda 2. And how would we express the the photon's energy? Well, we would say E2 equals hf2 equals hc over lambda 2. So, pretty interesting theory here. And then, of course, he runs the experiment and puts it to the test. And let's see what we ended up with for a conclusion. We start off with conserving momentum, which would be P before equals P after. Let's put it all together from the diagram. So we have the only objects that have momentum before are the incident X-ray photons, which have a momentum defined by h over lambda 1. What objects have momentum after? Well, you have our electrons, which have a momentum mass of electron times the speed, plus the photons, which have momentum h over lambda 2. So what should we see here? If all the original momentum is h over lambda 1, and then the original momentum gets imparted to both the electron and the photons retain some of their momentum, that means the original incident X-ray photons should lose momentum because it's giving some of it to the electrons. Well, if it's losing momentum, if there's a decrease in momentum, if P2 is less than P1, then what should we see happen to the wavelengths? Well, we see an inverse relationship between the wavelengths. So if there's a decrease in the momentum, we should see an increase in the wavelength. And what was found when Compton performed this experiment was that the wavelength did decrease after collision, therefore verifying that the conservation of momentum was true. So, pretty neat experiment showing that X-ray photons conserve momentum when hit with an object of mass, like an electron. In addition, we see whether or not energy was conserved. So EI equals EF. What objects, if any, had energy before? And of course, once again, that was just our photons, which would be HF1. What objects, if any, have energy after the collision? This would be our electron, 1/2 mv squared, me the mass of electron, plus our photons maintain some energy, so that would be HF2. Well, once again, if the original energy is equal to the energy after, that means the photons should lose energy because they're giving some of the energy to the electrons to be scattered. So what should we see here? Once again, we should see that that the frequency and therefore wavelength of the photons after collision changes. What should we see? We should see a decrease in frequency and an increase in wavelength like we mentioned above. So we should see a decrease in frequency. And when Compton performed his calculations, he found out, once again, that that was true. What was the purpose of all this? The big picture here is that he is showing that light, or members of the electromagnetic spectrum, because X-rays aren't light, but they're still a member of the electromagnetic spectrum, conserve momentum and conserve energy. Well, those are certainly particle-like properties. So this experiment gave a lot of proof and evidence to the fact that light is a wave. Alrighty, next we're going to take a look at the DeBroglie Matter Wave Theory. And in the DeBroglie Matter Wave Theory, DeBroglie kind of flipped it around and said, okay, well, if you're going to say that light acts like a particle, then I'm going to say that all particles have a wave-like nature. So we can see our particle with momentum p over here that has a wave associated with it afterward. So if we start out with our momentum equation, which was p equals h over lambda, what DeBroglie said was, well, I'm going to switch things around. If you're going to say that light is a particle and has momentum, then I'm going to say that particles have a wavelength associated with them when they move. Well, solving this equation for lambda, you can see we just switch lambda and p, so lambda would be h over p, which this would be h over m times v for particles that have mass and velocity. Okay. So I'm sure you've seen before, you've heard of before of Usain Bolt, the fastest human in the world, and I'm sure you've seen as Usain runs, okay, the wave that travels behind him, right? Well, let's prove whether or not Usain Bolt's matter wavelength is observable. In order to calculate his matter wavelength, lambda, we take Planck's constant and divide by his momentum, which would be the product of mass and velocity. Whenever you do DeBroglie's matter wavelength calculation, your Planck's constant always has to be in joule seconds. So we go ahead and we substitute 6.63 times 10 to the negative 34 joule seconds. We divide by Usain Bolt's mass. I went and looked it up. He has a mass of 94 kilograms. And now we need to know Usain Bolt's speed. Well, he is known to have gone 23 miles an hour. So if we set up a little ratio, 27 meters per second is 60 miles per hour, as x is to 23 miles per hour. We find, of course, by doing cross multiply and divide here, that his speed in metric is 10.4 meters per second. That's pretty good. 10.4 meters per second. When we go and calculate his wavelength, go ahead and perform that on a calculator. Pause the video if you need time to do that. We end up finding that his DeBroglie wavelength is 6.8 times 10 to the negative 37 meters. At this time, I'd like to ask you to go to the reference table, page 2 of the electromagnetic spectrum, and find out the member of the electromagnetic spectrum that is 10 to the negative 37 meters. So please pause this video and go do that. And what you find by looking at the electromagnetic spectrum on the reference table is that you can't find it. The smallest observable wavelength is in the order of 10 to the negative 14 meters or so, maybe 10 to the negative 15. This is very, very tiny and not observable. So, no, we cannot see Usain Bolt's wavelength as he runs. Does this mean that DeBroglie's matter wavelength has no merit? Actually, they found that electrons, when they move, give off a wavelength that's detectable in X-ray film. And there you have it.